Hey guys, this is Mrs. Rooker again. I'm going to have you do the review problems again, so pause the video and work on problems 1, 2, and 3, and then we'll go over them. Alright, so on number 1, we're supposed to solve for x. I'm going to rewrite this over here. We have x squared equals 1 over 2. We need to get x by itself, so we need to get rid of the squared. The opposite of squaring is square rooting. So that's what's going to get rid of the squared. Whenever we solve by square rooting, we need to put a plus or minus in front. So x is going to equal plus or minus the square root of 1 over 2. I'm going to break this apart into square root of 1 over square root of 2. And this actually needs to be reduced because I'm not allowed to have a root on the bottom. I have to rationalize the denominator. So this is going to be plus or minus 1 over root 2. To get rid of the root on the bottom, I have to multiply top and bottom by root 2. And I end up getting root 2 over, root 2 times root 2 is root 4, which is just 2. So that's the answer to that one. Find all of the zeros. To find the zeros, I'm going to first factor by grouping. So I'm going to put a line down the middle and factor out the first two. When I factor out the first two, I can take an x squared out. And then I'm left with, I divide this by x squared, divide that by x squared. I'm left with x minus 2. Which I then copy on the other side, x minus 2. And then I look at these two and I decide what I have to take out of 4x minus 8 to get the x minus 2. And that's a 4. So one of my factors is x minus 2, and the other factor is x squared plus 4. Then I set each of those equal to 0. So x is going to equal positive 2. And then x squared equals negative 4. Then we square root both sides. Remember to put a plus or minus in front when you square root. X is going to equal plus or minus 2i. Because the square root of negative 4 is imaginary. So your solutions, your 3 zeros are 2 and positive and negative 2i. All right, and then number 3, you're going to solve for x in each problem. I'm running out of room. And then once we solve for x, we're going to write a quadratic in standard form with those roots. So to solve this one, log base 2 of x plus 2 equals 3. I'm going to do the loop method. So I'm going to start with my base. I always start with my base. I loop to the other side of the equal sign. So that's 2 to the 3rd power. I always start with the base. 2 to the 3rd power and loop back to the other side of the equal sign. Equals x plus 2. 2 to the 3rd power is 8 equals x plus 2, and then subtract 2 from both sides, x equals 6. And the next one, I do the loop method as well. I start with 8, I loop to the other side of the equal sign, so it's going to be 8 to the 4/3 power, then loop back to the other side of the equal sign, equals x. I think other teachers call that left, right equals the middle. So left to right equals the middle is what we have there. All right, and now I have to do 8 to the 4/3 power. I'm going to rewrite this in radical form. So it's going to be 8, the index is going to be 3, and then 4th power. 8 is a perfect cube. The cube root of 8 is 2. So the 4th power is going to be 16. So x equals 16 and 6. that's not the whole problem. It's a long problem. We need to write the quadratic, or write a quadratic equation in standard form with those roots. So to do this, I'm going to write the factors are going to be x minus 6 and x minus 16 if the roots are 6 and negative 16 because they're opposite. But then it said that it needed to be in standard form, so to get it into standard form, I need to FOIL or double distribute. X times x is x squared. X times negative 16 is negative 16. Negative 16x. Negative 6 times x is negative 6x. And then negative 6 times 16. Negative 6 times negative 16 is going to be positive 96. Add together the middle terms, we get x squared minus 22x plus 96. Okay, so that is our answer. That is a quadratic equation in standard form that has roots of 6 and 16. All right, so the next thing I want you guys to do is pause the video again and try all of these on your own and try these without a calculator. So this should be a review of what you did the other day. So I'm going to go through these quickly. The first one I rewrote as log base 10 of 10 to the negative 4 power, because even if it's not written, we assume that it's a base 10. So that's why we have base 10. And then I wanted to rewrite the 0.0001 so it also had a base of 10. 0.0001 is the same as 10 to the negative 4 power. You can always do guess and check on that if you can't remember. But since this is the decimal was moved over 4 times, it's 10 to the negative 4 power. And then what you can do is, because we have log base 10 and exponent base 10 here, they cancel out. Whenever the log base and the exponent base are the same, they cancel out. All that we're left with is negative 4. So that's the answer on number 1. Number 2 is even quicker than that. We have log base e, because that's what ln is the same as log base e of e squared. We don't usually write it like log base e, we just write it as natural log. But log base e and regular base e cancel each other out, so we're left with just 2. So basically, natural log and e cancel each other out. All right, next one. I would rewrite this as natural log of e to the negative 15 power. Oops. 1 over e to the 15th is the same as e to the negative 15. To flip the fraction, we do a negative exponent. And then natural log and e just cancel each other out because natural log is log base e, and we have a base e here, so they cancel each other out. So our answer is just negative 15. On the next one, natural log and e cancel each other out. What we are left with is e to the first power. So really we're just left with 1 there. And then pi times pi. So 1 times pi is just pi squared. Next one. Same idea. We have base e. And then we have log base e, because that's what natural log is. Those will cancel each other out. We'll be left with 2 times 34, which is 68. The next one, what I would do first is, and we'll do more of this when we do expanding, but the rule is that you can bring the coefficient up as an exponent. So this is now 10 to the power of log base 10 of 7 squared. If there's no base written, we know that this is log base 10. So I should write that better, sorry. So really what we have here is 10 log base 10 of 7 squared. The big base 10 and the log base 10 cancel out. We're left with just 7 squared, or 49. If it's not written, we have a base of 10. So the log base 10 and the exponent base 10 cancel. We're left with just 17. All right, log base e and exponent base e cancel. We're left with 314 times j. 314j. Log base e, exponent base e will cancel. We're left with 8 times 8, so 64. Log base 17 cancels with exponent base, exponent base 17, so we're left with just w. This one's a fun one. Log base 5 of 5 is where I'm going to start. The log base and the exponent base are the same, so they'll cancel out. We'll be left with whatever the exponent was. The exponent was 1, so we're left with just 1. I'm going to rewrite this as 8 log base 3 of 1. Log of 1 is always going to give you an answer of 0. So that is our answer, just 0, because we had log of 1. All right, again here, natural log and base e cancel each other out, so we're left with just whatever the exponent was, which was 1. So we have 7 log base 10 of 1. Log of 1 is always just going to be 0. So that's my answer. All right, graph natural log functions and state the domain of the log functions. Be able to find inverses algebraically and graphically. So we're going to start by graphing the logs, and then we're going to write the equation of the vertical asymptote and state the domain and range. So when I do these, I convert to exponential form first, and I ignore the shifts. So I'm going to, I didn't mean to highlight that. I'm going to ignore the shifts and just convert to exponential form. I'm going to write this as y for now. Y equals natural log of x is what we're going to convert to exponential form. Remember, natural log is the same as log base e. We're going to convert this to exponential form. E to the y power equals x. So it's the loop method. Then I plug in values for my for my y, not my x, because I'm doing logs, so it's backwards. I plug in 0, e to the 0 power is 1. Plug in 1, e to the first power is 2.72. And then plug in 2, e to the second power is about 7.4. Then I'm going to graph those. 1, 0, 1, 2.72, 1, and then 7.42. The asymptote was originally going to be at 0, but if we have shifts, that will affect the asymptote. So we have a right 2 and up 3 shift, because left to right is always opposite. So we're going right 2 and up 3. So each of the points are going to go right 1, 2, up 1, 2, 3. So right 1, 2, up 1, 2, 3. Right 1, 2, up 1, 2, 3. The other thing that moves right 2 is the asymptote. And that's what our functions should look like. I'm supposed to write the asymptote is a vertical line, so it's x equals 2 is the asymptote. And then the domain is the x is greater than 2, which could also be written as 2 to infinity. It doesn't touch 2, so it's a parenthesis, not a bracket. And then the range is always all real numbers, negative infinity to positive infinity. Oops, did that backward. For the, so that's the range. Domain was, but it goes to the left of 2, or sorry, to the right of 2. All right, and that was it for that one. The next one is going to be the same thing in the beginning. So this part here is all going to be the same because it's a natural log just like this one was. So I'm just going to rewrite this really quickly. So I'm going to go y equals natural log of x. Natural log is the same as log base e. So I go e to the y equals x, which is the same as I had over here, which means I have the same table. So I'm not even going to rewrite the table. I'm just going to plot those points. 1, 0, 2.72, comma 1, and then 7.4, comma 2. But the shifts and reflections will be different on this one. So I'm going to reflect over the x axis because of this negative in the very front. I'm going to reflect over the y-axis as well because of this negative inside the parentheses. And then I'm going to shift up 1. So I'm going to do the reflections first and then I will shift. So I am first going to reflect the point 1, 0. When I reflect it over the x-axis, it doesn't change at all. But when I reflect over the y-axis, it becomes negative 1, 0. Then I'm going to reflect the point 2.7, comma 1. When I reflect it over the x-axis, it becomes 2.7, comma negative 1. And then when I reflect it over the y-axis, it becomes negative 2.7, comma negative 1. So it's over there. And then same idea on the point 2.7, comma 2. It's now going to be negative 2.7, negative 2. So that was the reflections. I still need to do the translation, the shift. Everything needs to get shifted up 1. So up 1, up 1, up 1. When I shift up 1, the asymptote does not change. The asymptote is still at 0 for the asymptote. Sorry, my organization is not very great today. So that's the asymptote. What else did I need to do? The domain is going to be, everything is less than 0 because it's on the left side of 0. So that's negative infinity to 0, or x is less than 0. And then the range is, it goes forever up and forever down, so that's negative infinity to positive infinity, or all real numbers, however you want to write it. All right, moving on. Domain of a log. The input of a log function must always be positive. So when given f of x equals log base b of x, set x greater than 0 and solve. So basically, what you need to remember for every single one of these domain and range problems, is that you need to set this greater than 0. So whatever the log is of, it needs to be greater than 0. Nothing else matters on these. Number 3 is pretty straightforward. It's just going to be x plus 2 has to be greater than 0. Subtract 2 from both sides. X has to be greater than negative 2. So it's basically just opposite of whatever that number was. This should be written in interval notation as negative 2 to infinity. Next one, same thing. We only care about these numbers though. We don't care about the number on the end. So this one's going to be x minus 4 is greater than 0. Add 4 to both sides. X has to be greater than 4, which could also be written as 4 to infinity. So it's just the opposite of the number that's inside the parentheses. All right, on the next one, it's a little different. We have that x squared is going to have to be greater than 0. I'm going to kind of do a visual representation of this. Remember, x squared is a parabola that has a vertex of 0, 0. So this is what x squared looks like, and we need x squared to always be greater than 0. So what that means is we need it to be above the x-axis. So everywhere up here is good. The only time that it's not acceptable is right here. When it hits the x-axis, that isn't allowed. So the only value that isn't allowed is 0. So x is not allowed to be 0, but it could be anything else. The reason is because x could be a negative number. Let's say x was a negative 2. This would be natural log of negative 2 squared. Negative 2 squared is 4. That'd be natural log of 4, which is allowed because that's a positive number down there. So the only number that doesn't work is 0, because that's going to make you have natural log of 0, which isn't allowed. All right, next one, I'm just going to take 6 minus x and set that greater than 0. To solve for x, I have to subtract 6. Negative x is greater than negative 6. Divide both sides by negative 1. When you divide by a negative 1, you have to flip the direction of the inequality. So x is going to be less than 6, which can be written as negative infinity to 6. The next one is another weird one because we have a squared. I'm going to write this as x minus 3 squared has to be greater than 0. I'm going to graph this one again. Remember, this here is a parabola, and it's in vertex form. This is a vertex of x minus 3 squared plus 0. This is a vertex of 3, 0. So when I graph this, the vertex is 3, 0. This parabola is opening upward, so it looks something like this. Which means this whole thing is positive the whole time except for right here. That's the one time that it's not positive. So the one time it's not positive is at 3. So that's the one time that it's not acceptable is at 3. So your domain would be all real numbers except x cannot equal 3. On number 5 back here, this should have been all real numbers. This should have been all real numbers except x cannot be 0. All right, and then the last one, best for last. Same thing. I'm going to set x squared minus 5x plus 4 needs to be greater than 0 because I can't have any 0 or negative logs. I need to factor this in order to solve. What multiplies to 4 but adds to negative 5 is -4 and -1. So this factors to x minus 4 and x minus 1. I'm going to do a graph representation of this again. This is in intercept forms. The intercepts are 4 and 1, and it's going to be a parabola. Because it's positive in front, it's going to be opening upward, and this is obviously a rough sketch of it. But this end and this end are positive. They're above the x-axis. This right here is no good. We are not allowed to have negative logs. So this part that I crossed out down here is no good. The only parts that are acceptable are to the left of 1 and to the right of 4. So that means to the left of 1 is from -infinity to 1. And then to the right of 4 is from 4 to infinity. So that is an acceptable domain. That's the domain. We put a little symbol. This is the union symbol. So it's from -infinity to 1 is acceptable, and then from 4 to infinity is acceptable. This could also be written as x has to be less than 1 and x has to be greater than 4 is the domain. Because anywhere else in it would be negative, which is not allowed. All right, the one thing I forgot to talk about on each of these was the range. And that's because the range on each of these, all of these log functions, is going to be all real numbers. So range is all real numbers for all of them. So -infinity to +infinity. All right, I think that is it. Thanks, guys.